Okay, so here we have a change happening at room temperature where the ice melts over time and makes a puddle of water. Is this change spontaneous? What that means is, does it just happen without any outside intervention? And the answer is yes. Is this process endothermic or exothermic? Well, if you're holding an ice cube, then the heat from your hand is being used to melt the ice cube. So that means this is endothermic. What is the sign of delta H? Well, for endothermic processes that are absorbing heat energy, the delta H sign will be positive. Now, if you're looking at this change at a molecular level, the water particles are extremely ordered when they're in the ice arrangement. And in order for it to become liquid water, where the particles are more freely and randomly moving, there's going to be a positive difference in entropy. So that means that the sign for entropy is positive because entropy is increasing. And is this process enthalpy driven or entropy driven? Well, this is going to be entropy driven. And the reason is because when you have a positive delta H from ice melting, because it's endothermic, as we said above, entropy is increasing, and this wouldn't happen spontaneously without the help of entropy. So therefore, this is entropy driven. Now let's talk about how this relates to the first law of thermodynamics. In the first law of thermodynamics, it says that energy is conserved. So energy can't be created or destroyed. So when something releases energy, because there's an exothermic change, potential energy that's stored in chemical bonds is now converted into kinetic energy, and that causes the atoms and the molecules to move more. And as the kinetic energy increases, then the temperature rises. Now, when something is giving off heat, that heat is transferred from the system. So the system is whatever we're studying, and then the surroundings is everything outside of it. Now, let's talk about spontaneous changes. So when we say that a reaction is spontaneous, that means the reaction occurs without any outside intervention. That doesn't mean that it happens rapidly. Okay, if I'm talking about a non-spontaneous event, then that will only happen as long as it receives some sort of outside assistance. Generally speaking, non-spontaneous events happen at the expense of a spontaneous reaction. So that means they will only happen if a spontaneous change occurs first. Let's take a look at the next page. So on the next page, I think did I go too far? Oops. No, we're good. So when some sort of a change lowers the potential energy of a system, it tends to occur spontaneously. And while a lot of spontaneous reactions are exothermic, there are some common examples of spontaneous changes that are endothermic. So when ice is melting, or when water vaporizes, or if you're dissolving salt in water, these tend to be spontaneous endothermic changes. So since each of these things are endothermic and spontaneous, there's something else that's playing a role in overcoming the unfavorable energy change. So if you take a look, then there's going to be an increase in randomness or disorder. And this is what led to something called the second law of thermodynamics, which says that entropy of the universe increases with every single spontaneous process. Now let's take a look at the quick check. We're going to use reasoning to decide which of the two options in each example will occur spontaneously. So in A, if you've got a mole of ice at 0 degrees Celsius or a mole of liquid water at the same temperature, you want to ask yourself which one has more disorder, and therefore that one will occur spontaneously. Well, the liquid water is going to have more disorder because the particles are more randomly moving. In B, solid sodium chloride at the bottom of a bucket of water or a solution of salt in water. Well, in the solution, the ions that make up salt are freely moving about. C, a collection of jigsaw pieces or the completed puzzle. Well, the jigsaw pieces would be more random. D, a kilogram of raw rubber or a kilogram of vulcanized rubber. So vulcanized rubber is actually like synthesized and it's more ordered. So you'd want to have the raw rubber. E, a pack of cards to arrange in suits or a pack of cards that's randomly shuffled. I would pick the randomly shuffled. Okay, now, Ludwig Boltzmann determined the probability of particles occupying certain positions in time. And the sets of positions that particles can occupy are known as microstates. Microstates are abbreviated with a W. I have seen this on the AP exam where they ask you about microstates, okay? And Boltzmann had an equation where, I'm highlighting the wrong part, sorry, where S is entropy, and this is going to equal his constant, KB, times the natural log of W, which would be times the number of microstates. Now, I have not seen this equation in application on the AP exam, so this is all I'm going to say about it. I'm just making you aware of it. Now, if you take a look at the next page, let's talk about how we define standard entropy. So if I have a pure crystal and I'm at absolute zero, which is 0 Kelvin, the particles can only be in one possible microstate. So we define the entropy at absolute zero as being 0 Kelvin. I'm sorry, as being 0 at 0 Kelvin. This is the third law of thermodynamics. So the entropy of a pure crystal at absolute 0 is 0. And this is what all of the standard entropy values in the back of your book in the tables are measured against, okay? You learned in a previous section that as we increase the number of electrons in something, you are increasing the number of, or if you're increasing the number of atoms, which could cause more twists in certain bonds and more positions three-dimensionally that those atoms could occupy, we are increasing entropy, okay? So the more electrons or atoms, the more possible microstates, and therefore the higher entropy based upon Boltzmann's equation. Now, the dependence of entropy on temperature, let's bring this up here, is the next section. So there are two kinds of disorder. There's positional disorder, which depends upon how the particles are arranged in space. And then there's thermal disorder, which has to do with the energy distribution within all of the particles, which would be different, okay? Now, if we add heat, heat is going to cause the particles to move more randomly, collide more often, be in different places. So adding heat to a system results in a greater disorder and therefore greater entropy. So entropy is actually going to be directly related to the amount of heat that is added. And if we're looking to calculate the change in entropy from the surroundings, that will equal the negative delta H divided by T, okay? And entropy is going to have units of joules per Kelvin, which is energy divided by temperature. If we're looking at a certain physical or chemical change, the units may be joules divided by Kelvin times moles. Let's go to the next page. Let's take a look at the quick check. So number 1 says you've got a mole of steam that's condensing to form a mole of liquid water at 100 degrees Celsius, and 40.7 kilojoules of heat is released. What is the change in entropy for the surroundings? So the change in entropy of the surroundings is going to be equal to the negative delta H divided by temperature in Kelvin. Now, since they told us that heat was being released, that means this is a negative 40.7 kilojoules, because that would be exothermic. So a negative of a negative would be positive. And then you would divide this by, add 273 to the degrees Celsius, so 373 Kelvin. And then when you divide this out, you're going to want to probably convert kilojoules to joules. And you're going to end up with 109 joules per Kelvin. Okay. Now for number 2, they want to select the example with greater entropy. So for A, you're looking at which one would have more electrons, or which would be Cl2. And then for B, you're looking for which one would have more atoms, which would be CO2. And then in C, obviously, the bricks on the right are more unorganized. Okay. Let's take a look at entropy being a state function. So entropy is a state function, which means it is not dependent on the path. You should definitely know that. I have definitely seen that in questions on an AP exam. And so what this means is you can use a calculation that's sort of like Hess's law to determine the entropy change of the reaction. So this means that you would take the sum of the entropies, standard entropies of the products, minus the sum of the standard entropies of the reactants. And if you have coefficients on anything, you would want to make sure that you multiply those coefficients by the standard entropy value. Okay. And if you have a positive or negative standard change in entropy, that will tell you whether it's a spontaneous or non-spontaneous process. So if the entropy change is negative, it's a non-spontaneous process. If you have a spontaneous entropy change, it will be a positive entropy. So let's take a look at the next page at the practice problems, and let's go ahead and apply this concept. So if you take a look at number 1, they want us to use qualitative reasoning to determine whether the entropy change is going to be positive or negative, and then whether it's spontaneous. So if you take a look at A, we're evaporating rubbing alcohol. Well, those particles are going to be more random, right? More randomly placed in the gas phase. So that's a positive change in entropy. And since it's positive, that means it's a spontaneous process. For B, I have one gas particle and no gas particles on the product side. So since the gas particles is decreasing, it's a negative change in entropy. So this would be non-spontaneous. And then for C, I've got one gas and then I've got 3 on the product side. So this is a positive change in entropy, which would be a spontaneous process. And then we're going to just skip D. Let's take a look at number 2. Use the standard entropy table in the back of the book to calculate the standard entropy change for each of the following reactions. Okay, so in the back of the book, CaCl2 and H2O have these values. And then CaO and HCl have these values. So to get the standard entropy change, it will be 104.6 plus 69.91, then subtract that for the reactants. But since there's a coefficient of 2 on HCl, you need to multiply 186.91 by 2. And then that's going to give you a negative 239 joules per Kelvin. And then here, since it's negative, this is going to be a non-spontaneous process. And then for B, these are organic molecules, which are in a table that's even further back in your book. So here we've got 229.6 for the C2H6, 219.56 for the C2H4, and 130.68 for the H2. So here your standard entropy change would be 229.6 for the product minus the reactants, 219.56 plus 130.68. And then this is going to be negative 120.64 joules per Kelvin. And since this is negative, this is also non-spontaneous.